So now we have come to the next session, last session in this class. So this is about ladder operators. So just now we were discussing about ladder operators L plus and L minus. L plus is given by this expression Lx plus ILy, okay, and L minus is given by Lx minus ILy. Okay, of course, very important thing that all are Hermitian operators. You have to remember this one. So Lx and Ly, of course, L plus, L minus, all are Hermitian operators. Only then we can get real values, real eigenvalues. So very important one. So here Lx and Ly are the operators for x and y components of angular momentum. L plus is called raising operator and L minus is called lowering operator. Okay. Now, very important thing is L squared and L plus, whether they commute with each other or not. L squared and Lz. Okay, if it means that separately you can measure. So L squared, L plus, if it commutes with each other, the answer will be 0. It implies that L squared can be measured separately, correct? They will commute with each other, and L plus simultaneously you can measure, not separately, simultaneously you can measure. Okay, it implies that they will commute with each other, so you can measure simultaneously at the same time. Okay, now instead of L plus you can substitute Lx plus ILy. So L squared Lx plus Iy can be written as L squared Lx plus L squared Ly, which is equal to 0. So similar relations for L squared comma L minus with a commutator, that also will be equal to 0. So it implies that L squared and L minus can be measured simultaneously. They allow simultaneous eigenstates. The same eigenstates will be applicable for L squared and L minus. Okay. Now commutation relations for Lz with L plus and L minus. So this is another one, another property. Lz comma Lx with the commutation relations can be written as L plus. Instead of L plus you can write Lx plus Ily. So Lz Lx plus Lz with Ly. You can write this one, correct? So now we have Lz comma Lx. Okay, we have Lz comma Lx. As I said just now, you will have to follow this cyclic rule. We have Zx, that will give you plus Ly. See, I gets cross plus Ly. Suppose if it is so, Lz Ly, say Lz y. So goes this way. Okay, so answer will be minus. Here it is plus. Is it okay? Because it follows cyclic one. Suppose it goes in the opposite direction, answer will be minus. So don't forget. So answer for this one will be I gets cross Ly. Answer for this one will be minus I gets cross Lx. Already one I is there. Okay, so that will give you I squared minus 1. So you will have plus h bar Lx. Okay, we can pull h bar out. So that will give you Lx plus Ily. Lx plus Ily, already we know that this is raising operator, expression for raising operator. So you have h bar L plus. So Lz operating on Lz, the commutator of Lz L plus will give you h bar L plus. Is it okay? So similarly you can have Lz commutated with L minus will give you minus I h bar L minus. So we have plus h bar L plus. Okay, then we'll have minus h bar L minus. We will see. Now Lz is there. Expression for L minus will be given by this expression. So Lz Lx minus Lz Ly. Okay. So we can write this as Lz. We can write this as Lz Lx. Lz Lx will be, come on. You have no plus only. Lz Lx will be plus. It's cyclic one. So this will have plus value. Lz Lx will be your I gets cross Ly. And Lz Ly. Look at this. Lz Ly. So that will be minus. So minus I gets cross Lx. Is it okay? So you have I gets cross Ly as it is. You have minus plus I squared minus 1. So minus h bar Lx. You pull minus h bar out in this expression. We will have Lx is here. Already you have pulled minus sign. So this will be Lx minus I Ly. Lx minus I Ly is nothing but L minus. So commutated with Lz L minus will give you minus h bar L minus. So combining this one and this one, put together we can write this as plus or minus. So this is your plus and this will be your minus. So we can write these two equations in one equation as L plus Lz comma L plus or minus. In commutator will give you plus or minus h bar L plus. Okay, is it okay? Equation 5.23. Now we'll go for commutation relations for L plus and L minus mutual. Okay, now we are going for these two operators L plus and L minus. L plus is given by this expression, L minus is given by this expression. Is it okay? So we have now four components. We have Lx, Lx with Lx, then we have Lx with this expression, and we have ILy with Lx, then we have ILy with minus ILy. Okay, so Lx comma Lx will give you answer as 0. It's very simple one. Similarly, Ly with Ly answer will be 0. So we have remaining two terms only. So we have now Lx Ly. What is Lx Ly? Lx Ly I h cross Lez. So minus I is there already. So instead of this you can write I h cross Lez. What about Ly Lx? Minus I h cross Lez. So we have I, this term is there. So we can minus I h cross Lez. So simplifying this term will give you h bar Lez. Simplifying this term will give you h bar Lez. So both the terms can be added. We'll have 2h bar Lez. Okay, L plus L minus will give you 2h bar Lez. So that's all. We have come to the conclusion. Physical signification of computation rule implies that three components, we have three components Lx, Ly, Lz of an angular momentum cannot be specified simultaneously. You can't specify Lx, Ly, Lz simultaneously. Okay, if one component is specified, then the other becomes uncertain. So you have to follow uncertain rule. So the commutative relation implies that any angular momentum L of a rotating microparticle can be represented by a vector with a precise length L with one of its components precisely defined. So we will be looking at now. Okay, by convention Lz is chosen. This is what I said. Lz, it was chosen earlier. Now also we are following the same thing. Lz is chosen. Why not Lx and Ly? They chose earlier Lx and Ly. So after the application of magnetic field, the reference axis is kept as Z. So that's why they have taken as Lz. So Lz is chosen to have a specific value so that Lx and Ly can't have specific values. Z axis is chosen as arbitrary axis. This is the reference axis for the magnetic field. When an atom or molecule is placed in a magnetic field, the direction of the field is chosen as Z axis. Okay. Now we'll just see two problems which are very important problems for your CSR examination. So that show that the raising and lowering operators are Hermitian conjugates. Okay, raising and lowering operators are Hermitian conjugates. That is, you have a raising operator and this will be lowering operator, the Hermitian conjugate. So L plus, which is equal to L dagger with minus, L minus dagger. Okay, we are going to show this one. So Hermitian conjugate of this will be this, Hermitian conjugate of this will be that. So Hermitian conjugate of raising operator will be lowering operator, Hermitian conjugate of lowering operator will be raising operator. That's all. Okay, so we are going to show this one. So now L plus sandwiched between your ket phi and psi, bra psi. Just think it off. Okay, we are going to have this expression. We are going to prove the Hermitian conjugate of L plus will be L minus. We are going to show this one. Okay, so we know that L plus is given by Lx plus ILy. So separate the equation as Lx and ILy. Okay, now we are going to change this one. When you are going to change this one, the moment we are going to substitute the complex conjugate, correct? We are going to change, see here, this is ket phi. Now it becomes bra phi. Bra psi, it has become ket phi, ket psi. Okay, taking the complex conjugate. Now take the complex conjugate, that will give you minus I. So you are going to change these two. So that will give you bra phi Ly ket psi with a complex conjugate, correct? So both are equal. You can write, combine together, you can write this as Lx minus ILy. Lx minus ILy will be L minus. So look at this one, L plus, and you have L minus. And here we have changed the components here, bra with ket with bra here, correct? So it means that L plus equal to L minus with a complex conjugate. Okay, so it implies that the Hermitian conjugate of lowering operator is nothing but raising operator, and vice versa. Okay, so we have shown this one. Now we'll go for the problem 2. So evaluate the commutator Lx Ly in terms of momentum representation. So Lx Ly, we are going to show this one in terms of momentum operators, momentum representations. And of course we know the classical expression for Lx is given by this. This is a classical expression which you have already studied in classical mechanics earlier. So Ly is given by this expression and Lz is given by that expression. We know already this. Now what is asked? Lx Ly with the commutator is asked. So Lx Ly with the commutator. So Lx Ly can be written as this is for your Lx and this is for your Ly. Okay. Now multiplying ypz zpx, correct? Then ypz will be xpz. Then zpy will be with zpx minus zpy will be xp. So we have 4 components now. Okay, first we will go for this pz. Here also we have pz, so this will become 0. First point. So we have one term as pz, the other term will be again pz is there. These two. So answer will be 0. Both will commute with each other. Okay. Similarly, we will go for this one z and z. Okay. Here also we have z. Here also we have z. Both will commute with each other. Answer will be 0. So this term, 2 terms will be 0. Remaining 2 terms we are going to find out. Okay. So this term can be written as ypz zpx. So this term can be written as you have pz here. Here also you have z. So we can write this as commutator pz, z. Remaining term you just pull it out. Is it okay? We have pz, z. Remaining term you pull it out. Similarly, the last term. Last term you have zpz. You have zpz. So zpz you pull other terms out. Pyx. What is pz, z? Of course we know that zpz is nothing but xpx. It's not the IH cross. We know already. Correct? We know. So now zpz will give you IH cross py. So similarly pz, z will be you minus IH because we have changed the term. Zx, px will be your plus. Px, x will be your minus. So that's the way it is. So now we have this will be your minus IH cross ypx. xpx will be IH cross. Px, x will be minus IH cross. So that's why we have written like this. So answer for this term will be this one. Answer for this one will be plus IH cross xpy. So combining together that will give you IH cross in the bracket xpy minus ypx. And of course this one is a momentum representation for your Lx, Ly. So this is the answer. So you just look at this term, everything in terms of momentum. So this is a momentum representation of commutator of Lx, Ly. So simplifying this will give you IH cross Lz. So it implies that Lx, Ly, Lz cannot be measured simultaneously. Okay. So summary, whatever we have learned so far is given by given in this slide. So this is what we discussed. The first one, the eigenvalue of L squared, eigenvalue expression of L squared is given by this expression, eigenvalue is given by this value L into L plus 1 h bar square, and the eigenvalue expression for Lz will be given by this expression. Eigenvalue of Lz is nothing but ml h bar. So this is what we discussed. Okay, so we know that about the orbital angular momentum. So as I said, suppose the electron revolves on the nucleus or the proton, then this will be like this, exactly like this. Your angular momentum will be always projected. So total angular momentum, your capital L will be projected. These are the components. Your Lx, Ly, Lz. Ly is missing. Okay, you have Ly. So Lx, Ly, Lz. So you have L. Okay, this is your Ly. L is the resultant one. This is your Ly. Don't forget. So something is missing. So we have learned Lz, Ly equal to minus IH cross Lx. Lx, Lz equals minus IH cross Ly. We know already, we have learnt. Okay. So this L will be Lx square plus Ly square plus Lz square. So this is exactly like this. You have a simple pendulum. Suppose if you take a simple pendulum, so it goes like this. Okay. And we have a conical pendulum. Conical pendulum is like this. You combine these two. Conical pendulum and simple pendulum. We combine these two. What we call this as, scientists say this is spherical pendulum. They say this is spherical pendulum. So you have a simple pendulum like this, we have a conical pendulum like this. Okay, just imagine these two. Put together, that will give you spherical pendulum. So what I am saying is, you just have specific value for simple pendulum, then rotate. Okay, then you have specific value, then rotate. So this is first rotation, and this will be your second rotation, and this will be your third rotation. You just change the direction. So that will give you this rotation and this rotation. So for a particular value of this simple harmonic motion, that is simple pendulum, then you are going to rotate conical pendulum. So first one will be your simple harmonic motion, simple pendulum, and second one will be your conical pendulum. Combined together, that will give you spherical pendulum. So this is what actually the electron is. Okay, so this is what actually electron is. So cone decides. So this is what we call cone. So this represents your L squared. So L squared will be Lx squared plus Ly squared plus Lz squared. Of course, these three components are there, and this is called vector auto model. So we are following only vector auto model. So spatial quantization. Okay, spatial quantization. So space is quantized. See, for a particular simple motion, simple harmonic motion, and you are going to specifically rotate with conical pendulum. So this is called space. Space is quantized for particular L, for particular ML. Okay, then another one. See, for example, if you take L equals 2, so your ML will be minus 2. So you have minus 2 here, so it's fixed. Then minus 1 will be fixed. Then 0 is fixed, exactly. Plus 1 is fixed here. Then plus 2 is fixed. So we have how many cones? We have this cone is here, and this cone will be there, and we have down also we have another cone, and for L minus 1 also another cone. So this is something like that. Okay. So we'll start today. We have learned today, very important one is the eigenvalue expressions of L squared and Lz, and the physical properties of L squared and Lz we learned, and also some ladder operators, some expressions for ladder operators. So thank you, students. We'll see in the next class. Bye, students.